In this video, we're going to look at problem number 1, which is an example of a photoelectric effect problem. So in this problem, it says light of wavelength 450 nanometers shines on a piece of aluminum, and the work function is 2.866 EVs. Will electrons be emitted? And if so, what would the velocity be? So I drew a picture. So here's my piece of metal. It's lithium. If you remember from chemistry, lithium has one electron in its outer shell. So I would expect its work function to be lower than that of maybe other metals. The work function is how much energy that you have to spend to release that electron. And so that energy is given to me in electron volts, and the first thing I have to do is change it into joules. So I'm going to go into my calculator conversion menu, and I'm going to say 2.866, and we're going to go find our EVs, electron volts, and we're going to convert those into joules. And that is 4.59 to the negative 19. So we'll write that down. 4.59 times 10 to the negative 19 joules. All right, so the incoming light has a wavelength of 450 nanometers. And so the question is this enough energy? Is there enough energy in this light ray to release this electron? So we need to turn that wavelength into frequency. So to do that, I'm going to use the wave equation. C equals frequency times wavelength, and that's the speed of light. And I'm solving for frequency, and my wavelength is given in nanometers, and this value has to be in meters. So I'm going to throw a times 10 to the negative 9 on there. And the frequency turns out to be, so 3 to the 8th divided by 450 nanometers, 6.67 to the 14th power. So 6.67 times 10 to the 14th, and that's hertz. All right, so now I can kind of use what I would call a conservation of energy statement. So these are all energy values, and these are all in joules. So HF, that comes from the equation E equals HF. This is the amount of energy you have due to the incoming light. H is Planck's constant, so that's going to be 6.63 times 10 to the negative 34. The frequency is this, so 6.67 times 10 to the 14th. I want to point something out. When I multiply these two numbers together, I can get a really different answer at the end. If I rounded this off to 6.67, or if I kept this number in my calculator like I'm going to do, the answer can vary greatly. So again, that's why it's important that you show your work. So this is the incoming energy, and then I'm going to have to spend this many joules, 4.59 times 10 to the negative 19, in order to dig the electron out. And then the question is, so that's minus the work function, do I have any extra joules? And if I have extra joules, that would give the electron kinetic energy. So let's see. So I have Planck's constant, so that's going to be 6.63 to the negative 34 times my frequency value, which is my previous answer. So I'm just going to multiply that, and then I have to subtract off my work function. So as you can see, I'm going to get a negative number. You cannot have a negative amount of kinetic energy. So what that means is that this is not enough energy in this light wave to release this electron. So the question is, are electrons emitted? No, it's not strong enough. So I actually didn't expect the problem to turn out that way. So I'm going to take a second and repeat the problem. So I need to have light with light that has more energy. So instead of a wavelength of 450, what if I changed this to a light wave that had a wavelength of 400 nanometers? So this would become a 400. So let me change that. So 3 to the 8th divided by 400 to the negative 9. That would give me a frequency of 7.5 times 10 to the 14. So let's see what that would do. So I'll take my kinetic energy, is going to be HF minus W. So my H is going to be 6.63 to the negative 34 times my new frequency value, which is here, so times my answer. So now I have 4.9725 times 10 to the negative 19 minus my work function, and now it looks like I do have enough energy. So minus 4.59 to the negative 19, and I have this much kinetic energy left over. That doesn't look like a lot, but an electron has a very, very small mass, and so this is enough to get that electron to be moving pretty quickly. So how do you find out the velocity then of the electron? So now I'm just going to use my kinetic energy equation, 1/2 mv squared. And again, your answer can really vary here depending on your round off error with the frequency. All right, so this is 1/2. Here's the part people always forget. What do I put in for m? These are electrons that we're talking about, so it's the mass of an electron. 9.1 times 10 to the negative 31. That is the mass of an electron. And then I'm solving for v squared. So that is going to be that answer. I'll say times 2. Then I'm going to divide by 9.1 to the negative 31st. And that would be v squared. And then we will square root that. And my electron is going to 89,941-ish meters per second. All right, so I hope that helps you with a photoelectric effect problem.